So in this video, we're going to continue our work on solving equations, and we're going to introduce a couple new objectives. We're going to need to understand that there's many ways to express the same quantity, both in arithmetic and in algebra, and keep that in mind as we go through the course. And then we're going to simplify sides of equations to make our decision making easier. And that's going to be based on the fact there's lots of ways to write the same amount. Why don't we pick the most convenient one? So taking us back to the last video, equations told us that two quantities are equal. And sometimes you don't need a whole lot of indication that two things are equal. Right? We know that 8 plus 8 is the same thing as 16 is. But the equation just kind of reinforces that. But it's more important when you have an unknown quantity that you somehow know the value. Maybe it's a value that you're shooting for. Maybe it's a value that someone else told you it was. So t plus 2 being 16, that's not obvious on its own, right? But if someone told you that was true, then it's a really powerful tool because you can start figuring out what an unknown piece is if you have an equation. So numbers can be expressed a lot of ways is something else to keep in mind. And numbers like 16 can be expressed as 8 plus 8. They can also be expressed as 7 plus 9. What you want to do, though, I think, is you usually want to have the most convenient approach. You don't say that, how much is this dinner going to cost? It's going to cost us 7 plus 9. You would say it's going to cost us 16. That's the most convenient approach. So you use, there are lots of ways to represent the same number, but you use the one that's convenient for your job. And if your job was solving an equation, I don't think that saying that t plus 2 is equal to 7 plus 9 is the easiest way to say what you know. I think if we knew that, it would probably be easier for us to say that t plus 2 is equal to 16. So what this looks like then is you're calling it simplifying. This is an equation that for somehow we knew. And then this is an equivalent equation that wasn't found by using inverse operations. It was created by simplifying one side of the equation, saying, well, can't we say this side of the equation is just 16? So if t plus 2 is really equal to this, isn't t plus 2 equal to 16? And we're in a better spot now to use inverse operations. As it says here, you simplify a side of the equation like we did, and that makes our decision making easier. Getting t by itself will be a little bit easier. It also turns out that unknown expressions that have unknown values to them, they can be written lots of ways too. For example, because we don't know what x is, we don't know what x plus 4 plus 6 is. So that's an unknown quantity. But if we think about it and we knew that x was originally there and then they added 4 to it, and then for some reason they took that result and added 6 to it, thinking about how that relates to the original, well, if x was increased by 4 and then increased by 6, isn't it simpler to say that it was increased by 10? X was increased by 10. So this, again, is a simplified expression, and this time it's an unknown expression. It's it's an expression with an unknown value that's been simplified. So once again, if that was in an equation, I think it'd be easier to deal with this version of it. So this would be another case where we could simplify the left-hand side of the equation to come up with an equivalent equation. Notice it doesn't matter. You can clean up the right-hand side, you can clean up the left-hand side to come up with an easier equation. So let's look at two particular kinds of ways to simplify unknown quantities. The first one is going to be the distributive property. And the way that we're going to introduce the distributive property is we'll just pull, what would it say in a textbook or a formula sheet or something like that? It would say, well, here's what we mean by the distributive property. Okay, all right. So you're telling me that if I have an amount that is equal to a sum, order of operations tells me I would have to do that first, times a number, that you could rewrite that as this. Okay, so this starts to look intimidating, right? A couple things we do to try to take this out of the abstract, because this looks really abstract. I can remember learning this the first time and being intimidated. Some people will first say, well, why don't we make this more concrete by showing you a visual? It says if there's one term that you're multiplying by two terms added together, another way you could handle that is instead to distribute the multiplication, multiply the a by this part, multiply the a by this part, and then at the end do the addition. So these little arrows here, you'll see a lot of people draw them when they're getting rid of parentheses. When they're rewriting something with parentheses, you'll see them draw arrows like that. And that's the way to make it more concrete. Another way we could try this is we could talk about a real world use of it. People who do mental math, a lot of times they use the distributive property. I don't know what this looks like to you, but if I asked everyone in the room, what is 2 times 24? Some people are going to be very quickly able to come up with it out on the top of their head. Some people will use paper. Some people would have to use a calculator. But the people who are doing it off the top of their head are probably thinking this. Well, 2 times 24, what I'll do is I'll double the 20 and I'll double the 4. And when they do that, they very quickly come up with 48. But let's look at what they did. What they did was they thought of 24, I'm thinking of it as two parts. I'm thinking of 24 as a 20 plus a 4. The structure looks a lot like what I had described earlier. And the person who said they would double the 20 and then double the 4 and add them together at the end, they're actually distributing the times 2. So they're doubling the 20 and they're doubling the 4, and then they add them together to get 48. So yeah, the distributive property actually is a nice tool for mental math, but it's really important. You can do mental math without it, but in algebra, it's really essential. So we're going to show how we would use that here. We're going to solve this equation. 4 times the quantity x minus 5 is equal to 20. So this is the structure where the distributive property could be used. Doesn't need to be, but it could be. And if you're going to use the distributive property, your thought should be, I see an equation with parentheses in it, 1 term times 2 terms. I know that multiplication distributes over addition or subtraction. So this times 4 could be distributed to the x, 4 times x is 4x, and to the negative 5. 4 times negative 5 is negative 20. So this side of the equation, we just simplified it. So this is this has the same exact value as that does. So if we knew this equaled 20, then we knew this new line we just wrote equal 20 also. So notice we've written an equivalent equation, not by using inverse operations, but by simplifying one side. But at that point, the inverse operations become really clear. We would add 20 to both sides. We'd see the canceling on the left that inverse operations always affords us, leaving with just the 4x right-hand side. And notice this habit I'm trying to get everyone to follow is, write your new equation down completely, just under what was there before. So you could do this next thing, and this 4 times. Now if they're using an inverse operation to get rid of 4 times, that would be division. Show what I'm doing, a nice balanced inverse operation to both sides. So my new equation is going to be equivalent. My 4 times and my 4 divided by, they'll cancel, leaving me with x, and the right-hand side, whatever value 40 times divided by 4 is. So x equals 10 is the solution to this original equation, and to this equivalent equation, and to this equivalent equation. And that was a use of the distributive property. Another way we can rewrite unknown values, unknown expressions in simpler ways is combining like terms. So combining like terms is actually, in its formal way, it's another look at the distributive property. But when you use it is when you are given an equation or an expression, and you notice that there's a lot of addition and subtraction in one of your expressions, maybe more than we should have, because there's a better way to say I had 6 x's, and as I was building my quantity, I took away 8 x's. Because we could probably think our way through that. If I had 6 x's and I took away 8 x's, I know first thing that's going to happen is those x's are going to disappear. And I guess what will happen is we'll have some leftover negatives. Let's see how it plays out. If you think about this as the distributive property, what you do is you notice they're like terms. You use the commutative property, like we saw in the earlier video, and we just rearrange the terms carrying their signs with it. And then now this 6x minus 8x, some people look at this as almost, it looks like the x had been distributed. The same way the 4 found its way into both terms here, we distributed the 4. People look at this as if I distributed an x in, so they kind of undistribute the x. And when they undistribute the x, they get here, and it starts to tell people, look, there are negative 2 x's on that left-hand side. I don't like starting my explanations that way. At the beginning of algebra, I would probably instead suggest, let's think about like terms this way. Same scenario, left-hand side, 6x minus 8 x's. If I have 6 of something, x's, and I take away 8 of those things, I'm going to have negative 2 of those things, as I kind of laid out earlier. So the left-hand side, another way to write it is this. I think that's a lot easier than thinking about the distributive property, with all respect to the textbooks you read. So the left-hand side was equal to 14. I just wrote a new version of the left-hand side, so that's equal to 14 also. And now the inverse operations become more clear. Look at where x is. Look at all the layers that were put on it. This last layer is the first layer to go. Inverse operation for addition and subtraction. You know it's going to cancel here, so we should just have negative 2x on the left-hand side, and we get the result on the right. Now we have to undo this last operation, and understand this is not a minus 2. We do not use addition to undo this. This is a negative 2 times x. Really important you recognize that. So getting rid of times, just like we did over here, is going to be with division. I'll divide by negative 2 on both sides for a nice balanced inverse operation, so I can get x by itself on the left. And the right-hand side poses some challenge because 11 doesn't divide by 2, but that's a good time to use a fraction maybe. Say, hey, 11 was going to divide by 2. It wasn't going to work out nice. I left a fraction. Or you could grab a calculator and do your 11 divided by 2, negative 11 divided by 2. Or you could do a mixed number if you like. So in this video, then you've seen how, and then especially the tail end here, you could use the distributive property to simplify the side of an equation before you use inverse operations, or you can combine like terms to simplify the side before you use inverse operations. And you'll have plenty more work with that over the coming days.